I am live. Uh, Sorry, I have uh, two different monitors. The StreamYard stuff is on that monitor, so if I'm looking in that direction, it's because I'm looking at Streamlab stuff. If I'm looking in this direction, it's because I'm looking at the telescope interface. And so, um, howdy all. Welcome tonight. This is kind of last minute. I don't know how long I'm going to be doing this because I don't know whether or not the sky is going to cooperate. As you can see from our video or our views from our webcams, that the sky is pretty cruddy. And so it may be already too late, but I'm going to try anyway. So, we're going to try that anyway. So let's get some mood lighting. That is not the right color. That's the right color. There we go. Nice and red. I know I'm dark, but honestly, it's the monitor lights are pretty bright anyway, and I like observing where I can keep my night vision, even if I am not actually observing at the telescope. Just a quick piece of information: if you're ever at an observatory and you wonder why there are red lights everywhere, it's because of light adaptation. And let's see here. And I hope the sound is good. I know lately I've been having problems with my audio, particularly on the streams, but hopefully this is working out. But anyway, back to the red lighting. The reason why red lighting is often used in public observatories is because of the fact that the astronomers want to keep their dark adaptation. So when you turn off the lights, you may have experienced this yourself. When you're in a bright room and you turn your lights off, everything appears to go pitch black for a few moments, maybe even a few minutes. And then eventually, assuming that there are no other lights going on, what you have is you can start slowly making out your environment. You can start slowly being able to see relatively in the dark what D&D folks would call low light vision. And the reason for this is because of the fact that your retina is a biological camera, and that biological camera can become what we refer to as saturated, meaning that the sensors that receive photons or receive light particles become overly stimulated, and they cannot take any more information in. And so when they get to that point, when you turn the lights off, when you stop stimulating them, they need a little bit of time to readjust. They need to basically calm down, get rid of all of that background noise, and start being able to take in the limited amount of light that's already present in the room. When you look at the wavelengths of light from what we can normally see, which is basically the rainbow pattern of color, blue is more energetic than red. And so if you want to keep the stimulation to the receptors on your eyeball to a minimum, you want to observe solely in red light, or primarily in red light, because that still allows you to see, but it also aids in keeping your dark adaptation, allowing you to see in minimal or low light conditions. All right, so that being said, what I'm going to do is, as you can see here are the webcams that we use. There's the 32-inch or 0.8 meter telescope that we have here at George Mason. This is essentially the outside view, and you can see it's pretty darn cloudy out there, or what I refer to as soupy. This little thing here is probably a spider web of some sort. Let's go ahead and open up. Actually, take that back. First thing you want to do is we want to check the weather. Not only to see whether or not it's cloudy, but seeing if it actually is going to rain. First thing I check is to see whether or not the humidity is cooperating. Right now it's around 76%. If it gets around 80-85%, there is a chance that water will begin to condense onto the optics, which is always a bad thing. Now, let us go to fair. Just love that. Let's go. So this is the National Oceanic yada yada the weather National Weather Service, National Oceanic and Atmospheric Administration. That's the one. I know NASA. I don't know NOAA. Let's see. Oh, thanks, Alan. Looks like there are no. There looks like there are no rain in the vicinity. All right, chances are low, and then of course, this is the clear sky clock. This is the clear sky clock, folks, and I don't really know who does this, but they are fairly good. They are probably the most accurate weather determining tool I have really ever encountered, although of late they've been a little bit more spotty. But you can see here is you have cloud cover, and as you can see, it's going to, according to Clear Sky, it's going to clear out for about an hour around midnight. So I guess we're here at 9:30. So it's going to get a little cloudier and then clear out around midnight, and then it's just going to go to pot for the rest of the evening. The transparency, that's essentially how easily can we see. Oh, you know what? You know what I've been forgetting to do? I've been talking, and I've completely forgotten to actually share my screen. So you actually know what I'm looking at. Okay, so this is the clear sky clock. You can see there are essentially these clear sky charts for any number of observatories around the world. So if you're curious and you happen to live near an observatory, you can find the observatory near you and check out its weather. Transparency, that is essentially how well transparent are the clouds, if there are any in the night sky. So not only can you have cloud cover, but the cloud cover itself can be variable in its essentially obstructiveness. You can have, there are nights when, so partly cloudy can mean one of two things. One, it could mean that you have thick, dense, localized clouds in small areas around the sky, and so you can have large chunks of the sky that are open to view, and then periodically or regularly you can have your view completely destroyed or completely obstructed. Or you can have a whole lot of high altitude cirrus, which is what we're having tonight, which means that you might be able to punch through if the cloud layer is thin enough, but you're not going to get the best views possible because you still have a little bit of cloud cover, which is obscuring the night sky. Seeing that has to do with the quality of your observations. Depending on what kind of observations we're getting, I'll get more into what seeing is later on. But I think we're good to open. So I'm going to go over here and I'm going to open up the telescope. And maybe it will actually open. Yes, it is. All right. Well, at least it's telling me it's open. If we look down here, we can, if you're eagle-eyed, you can see the back end of this slowly sliding back, or the top of this slowly sliding back, and eventually this thing will flip open. And so that's what we have here. All right, I don't think anyone is actually watching, so I was going to ask while this is going on if folks had any questions, and I probably should just keep looking here. If folks have any questions, then I would be happy to answer them, but because no one's watching, there are no questions. There is no spoon. So I will just ramble on a bit until we're good to go. So what I am hoping to be able to look at tonight are astronomical objects known as globular clusters. I am very fond of saying that I believe the universe to be both lazy and social, meaning that from an astronomical point of view, uh, you are more than likely going to find astrophysical objects or astronomical objects in groups than you are singly just in space. So, for example, stars, over 50% of stars, and over 50% of stars a little bit, are in either binary companions or binary systems or higher order systems, meaning that you have a binary or two stars which are orbiting around a common center of mass. Or you can have triple systems where you have three stars that are orbiting around a common center of mass, or four stars, or five stars, and so forth. And it actually gets a little fuzzy as to where higher order multiple star systems exist to where they transition into what we call star clusters. Star clusters can range, depending on the type, anywhere from groupings of stars that are all orbiting around a common center um, on the order of tens to hundreds, all the way up to what I'm hoping to be able to look at tonight, which are globular clusters, which can have hundreds of thousands or even millions of components or stars orbiting around that common center. And so I think I say that phrase a lot. Anyway, um, globular clusters are some of the oldest structures in the universe. And in fact, back when the Hubble constant, or the age of the universe, was fairly contested in the sense that we didn't know the age of the universe plus or minus 50%. It was actually kind of embarrassing. The error bar on that age was ginormous. There were some proponents who believed that the age of the universe was actually younger than other methods were telling us that the ages of the stars in globular clusters were. So, for example, the globular clusters in the Milky Way galaxy are roughly around 10 billion years old, give or take. And maybe I'll do a Rob World episode, which will talk about how we actually determine the ages of star clusters. Primarily, we use something called the Hertzsprung-Russell diagram. We plot up the luminosities and the temperatures of these stars, and we look to see where the pattern of stars turns off, where essentially the stars, at what point do the stars begin to evolve into late stages of, well, evolution, or move from adulthood into, shall we say, more mature aged stars. And so, there you go. I said it again. Where was I going with that? So yes, I hope to put out a Rob World episode where I talk about that in a little bit more depth. But for now, just you'll have to take my word for it that we know the ages of these globular clusters, probably within 100 or 500,000 to a million years, or excuse me, higher or worse than that, a few hundred million years to maybe plus or minus a billion years. So, from an astronomy point of view, the ages of globular clusters is pretty well determined. I know it may not seem that way, but anyway, the dome appears to be open. So we are going to move to our first object. And see what we can see. And so the first object I have listed, or the first object I want to go to, is M13, or Messier 13. And this is a great cluster in Hercules. It's one of the most numerous globular clusters which are orbiting around the outskirts of the Milky Way galaxy. If you want to Google Messier 13, actually, well, I can do that for you. If you Google it, Messier 13, you can get nice, pretty pictures of it. See, the reason why it is called the globular cluster is because of the globular shape that it has. The globular shape is that there is so much mass located in this relatively small region of space. For example, this region of space is only on the order of few light years across. So, from an astronomical point of view, that's a very localized area. And so, given the amount of mass in that localized area, the stars are distributed in a spherical distribution. Because the more mass you have, the more sphericity something is going to obtain. And you can see that there are stars of a variety of different colors. The ones that really, for me, stand out are the red ones. Because these stars are so old, they tend to be more redder in color than bluer. But there are some bluer star components in there. Most likely, these blue stars are what we call blue supergiants, and they are stars that are essentially in the very last stages of evolution before they go supernova. All right. So that's what we're going to be looking at is M13. So I put in find M13. It found it right there with the red reticle. And I'm going to slew. Oh, I am going to unpark. And then I'm going to slew. And so you can see is that the telescope is going to move. And what I'm going to also do is I'm going to sync the telescope or sync the dome to the telescope. And so now the opening of the dome, or the slit as we refer to it, the slit of the dome will now move in front of the telescope, and it will stay there as the telescope tracks the night sky and continues to follow the globular cluster for as long as I tell it to follow it. The speed at which it does so is almost 15 degrees per hour. Thanks, Bob. The speed of the stars as they travel across the sky is actually slightly faster than the speed of the sun as it travels across the sky. And that has to do with the fact that the sun is also orbiting around the Earth is also orbiting around the sun as it rotates, as folks like to point out. The actual period of rotation for the Earth is 23 hours and 56 minutes. That is known as the sidereal day. That is the time it takes for one particular star to go from the meridian, or directly overhead, to a setting position all the way around the other side of the world, to a rising position, and then back to that same point directly above your head. That is known as a sidereal day, and that is 23 hours and 56 minutes. So if you divide that by 360 degrees, you get the rate at which the star or the Earth is spinning in terms of angular revolution. So technically speaking, the Earth does not revolve at 15 degrees per hour. It's a little bit slower than that, or a little bit faster than that, if I do the math in my head correctly. So it's not just 24 divided by, or 360 divided by 24. So there is a 4-minute discrepancy. The solar day is also known as a synodic day. All right, so I think everything is properly positioned. So now is the moment of truth, and we will see whether or not the sky is cooperating. And so I really hope so. I really would like some nice, pretty pictures to work on. All right, well, one thing I'm looking at is the cooler power. So one of the things that we have to worry about is noise from the camera. The camera, the sensor of the camera can actually detect slightly into the infrared part of the electromagnetic spectrum, or in other words, heat. So the camera can literally pick up heat. And so in order to mitigate that, we want to cool that camera down as low as we possibly can. Now, unfortunately, we are limited in the type of cooling that we can do. At this point, the camera can only be cooled electronically. We are contemplating the idea of water cooling the system, but that's something to be done in the future. But right now, it can only be cooled electronically. That can still get us down to temperatures like minus 30 degrees Celsius. However, it has to work pretty hard to get down to those temperatures. And unfortunately, if the day is warm, if the surrounding environment is warm enough, the cooler power is insufficient to really get us to that particular temperature. So we have to ease off a little bit. And so even in minus 25, it's getting it's working a little bit too hard. So I'm going to warm up the camera to minus 20 degrees Celsius and see if that helps anything. And while it's doing that, drum roll, let's take an exposure, not a 90-second one. I'm going to do it in the green filter because I always go to green. And we're going to take a picture. Okay, that doesn't look great. Great. Because I can see basically one star up here, maybe something over there. Make sure that there's nothing going on. But everything else is pretty washed out. Let me do a 30-second exposure, and we will go from there. I do have a backup for what I wanted to do if this proved to be a no-go. I wanted to do a little bit. I'll basically just do what is in the night sky for the next 2 weeks, depending on where you are in the northern hemisphere. Southern hemisphere, I could do it. I can show you what the southern hemisphere looks like, but I don't know what any of the objects are. Yes, I have an extremely northern bias, and that's even worse. Wait a minute, hold on. That's even worse. Oh, that's poop-tacular. Hold on. I think I might know what's going on. Yep. That's just all kinds of poop. All right. Let's make sure that I'm actually pointing at something and go to Vega. That should be bright enough to be able to be seen. Let's make sure the telescope is pointing properly. That's not what I want. That's what I wanted. And so yeah, I will go to a few locations in. Oh, I guess it's already there. I will show you what the sky looks like in the Eastern time zone, the Central time zone, the Mountain time zone, and the Pacific time zone, and what it looks like if you're in the UK. But I think that this is going to be a dud. And sadly, that's a thing in astronomy, is that while weather is weather is hard to predict on large scales anyway, but it's even worse on actually smaller scales. So while it might say that it's mostly clear or fair, its chance, or it potentially could be that it's really just a whole lot of clouds. Although I am suspicious. No, that looks pretty soupy. Hold on a second. Yep. that is completely overcast. So, clear sky clock. You lied to me. You said it would be clear. I know it wasn't going to be transparent, but you said it was going to be clear. And this is nowhere even close to being clear. All right. So, what I'm going to do is, I guess it might be a good thing that that no one is watching. But what I'm going to do is I'm going to shut all of this down. And let's see here. So let us take that off and home that. Well, no, park that. Let's abort. Okay. Hopefully I didn't break it. Okay. Dome is parking. So yeah, once I have this, once I get this put to bed, or mostly put to bed, I will bring up a program that I like to use called Stellarium, and I will show you what's in the night sky in the next couple weeks. So if you are watching this after the fact, you could probably just fast forward for the next minute or two while I'm doing this. All right. Closing the dome. I am going to park the telescope. Oh, hi, Surf. Sadly, the night is not cooperating. And so I thought that I would have at least an hour or two of reasonably clear skies in order to get some kind of pictures. But unfortunately, that was not the case. And so I am putting everything to bed, and I will be looking at, basically, I will be just showing a simulation of what the night sky looks like at various parts of the Northern Hemisphere for the next couple weeks. So, oh, and they left. So, Jade. All right, well, that's doing that. I don't need to worry about all right. Let's all right. All right, so I am going to stop sharing this, and I'm going to open this up. I think I'm going to turn that off. No, I am not going to turn that off. Okay, and so I will share that screen. Hopefully you can all see this. And what I've got here is a program called Stellarium, which, if you're unfamiliar with it, it is a free program which you can use. And actually, there is a web-based version of it, so you don't even need to download anything. And what you can do is you can put in your location on the Earth, and it will simulate what the sky looks like at any time of day or night that you might be interested in. And so for the next probably half hour or so, I plan on just kind of going through and explaining what you can see in the night sky over the next couple of weeks. And so I'm going to start off in my hometown, well, in the town that I'm currently living in, and that is Fairfax, Virginia. And I'm going to zoom out a little bit here so you can see the entire sky. I'm going to show that what I'm looking at, whoops, wrong one. As you can see, make sure that I've got the right date. The current date is the 25th of June, and it is 1 minute past 10 o'clock in the evening here in Fairfax. And so I really wish the night sky looked like that right now over our telescope, because if that were the case, then I would be taking nice images of globular clusters at the moment. But what you can see is we have a few stars that are highlighted. You have Arcturus in the constellation of Bootes, or Butes, depending on how you want to pronounce that. You got Vega in the constellation of Lyra. You have Altair, and then actually the star. I'm surprised they haven't listed Deneb, which is this star right here. And these three stars, the reason why I'm surprised it's not listed is because these three stars make up what we commonly refer to as the summer triangle. If you can see these three stars, they are very bright, they're very conspicuous, and you look up and they're basically maybe a hand's width away from each other. So your hand outstretched could fit between Altair and Vega, and actually that might be an underappreciation. But there's a giant triangle in the night sky, and that is called the summer triangle. And if you can see that triangle, then you know that you have just woken up from a coma and you are in the summer months. It is currently in the summer. So to guide our eyes, I'm going to put in constellation lines. So you can see again, this is Vega, which is a constellation of Lyra. You have, this is the Northern Cross, which is a smaller section of Cygnus, the swan. And then you have Altair, the eagle. Now, a fun little thing, and I'm curious to know whether or not the art displays it, and it does not. A fun piece of trivia is the three birds which comprise the constellations that make up the summer triangle are Cygnus the swan, Altair or Aquila the eagle, and in the German representation of the constellations, the Lyra, which is Greek for lyre, or basically a lap harp. In the German representation of the constellation art, it's actually held in the claws of a vulture for some reason. I'm sure there is some vulture within the mythology that I'm just not familiar with. So let's get that back out of the way so we can actually concentrate on what's in the night sky. So you can see you have three these blue areas. You have the June Boutids, the Junes Scutids, and the Ophiuchids. These are meteor showers, but unfortunately, they're not very popular. They're not very bright, and they're not a lot of meteors that can come in. For example, depending on the year, you can have anywhere from no meteors showing up on this part of the sky to 100 per hour. So it's highly variable. The Scutids, you're basically going to see a meteor every 2 to 4 meteors per hour. And in the Ophiuchids, you'd see around 6 or so. But again, these are, if you're really in a dark sky, you'd be able to see them. Now, what if you have a telescope? Before I do that, if you're in a dark sky, the other thing that you'll be able to see right near the end of the beginning of the evening is the Milky Way galaxy. And so you would see it as this bluish sort of cloud or band across the night sky. And it would be in the eastern part of the sky, and it will be rising throughout the night. And so As we move through the first couple weeks in June, or excuse me, the first couple weeks in July, the Milky Way galaxy is going to be in the eastern part of the sky, and it's going to rise, it's going to move westward over the course of the evening. Now, as a matter of course, no matter where you are on the Earth, every day, subsequent day, the stars that are in the east are going to appear higher up in the night sky at the beginning or at a particular time. So, for example, Altair at 10 o'clock on today has an altitude of around 21 degrees, meaning it's roughly 20 degrees above the horizon. Tomorrow at 10 o'clock, it's going to be slightly higher in the night sky. And that has to do with the fact that the Earth is orbiting around the sun. Because of the Earth's orbital motion, the stars that we can see in the night sky change depending on the time of year. So, for instance, the summer triangle is appropriately named. One of the few reasons why, or one of the few examples of where astronomers, probably the ancient Greeks, actually named something appropriately. Not very imaginatively, but it's appropriate. The summer triangle can only be seen in the summer. During the winter months, the summer triangle is actually only up in the sky during the day. And so the sky brightness of the sun washes it out completely. So you will not be able to see Vega, for example, in the middle of December for whatever reason. And so when astronomers are trying to figure out when they want to, when to best look at certain stars, for example, if I wanted to study the Ring Nebula, for example, if I wanted to figure out what its expansion rate outward was, I would need to plan my observations during June, July, and August rather than in December because of when it is most available. Now, because of the the reason why I really pointed at the Milky Way, again, I have found in my experience that the Milky Way galaxy can really be seen in a rural environment. You don't need a truly dark sky in order to see the Milky Way, although in a rural environment, it's more going to appear like kind of patchwork clouds, to the point it's very easy to mistake what you're looking for as clouds, as opposed to what the Milky Way the Milky Way galaxy itself. But if you're in a dark sky, if you are nowhere near civilization, if you're nowhere near streetlights, like for example in by God, West Virginia, or deep in the Arches National Park in Utah, the Milky Way galaxy it's clearly defined. You can even see the dark spots or patches within the Milky Way galaxy, which correspond to massive interstellar dust clouds, which are blocking the light from the background that we see. And so that white cloud is actually, as I mentioned in a previous stream, the white cloud of the Milky Way that we're seeing is in fact is thousands of stars all very, very close to each other. And so while we can see the light coming from the stars, our eyes are not sufficiently large enough to be able to resolve that whiteness into individual little stars. If you have just a low power pair of binoculars, that can actually easily do it for you. If you point your binoculars at the Milky Way, you can see the whiteness for what it truly is, which is just a vast collection of stars. If you move away from the Milky Way and look at say the western part of the sky during this time, the field that you'll see some stars, obviously, but you won't see nearly as many because of that. But one of the things that follows along with the Milky Way are open clusters. Now, at the beginning of this stream, I talked about the fact that stars are social creatures. They tend to group in clusters. They tend to not only be in binaries and triples and quadruples and septuplets and so forth and so on, but they also tend to hang out in clusters anywhere from hundreds or thousands of members to millions of members. Now, what we find is that clusters can be generally classified as either open or globular. Now, globular clusters, again, at the beginning of near the beginning of the stream, I showed an image of M3 or M13, excuse me, which is a huge, lovely globular cluster. There are so many stars within that cluster that it takes on a spherical shape, that it takes on a spherical distribution of stars. Open clusters, on the other hand, only correspond to about 100 or 1,000 stars or components. And so there's not enough mass for the stars to essentially rearrange themselves into a spherical distribution. They're much more open. It's a much more irregular pattern, and it takes up a larger part of the night sky. Open clusters also tend to be younger than globular clusters. And so what we find is when we look at the Milky Way galaxy, here, as I said, the cloudy part of the Milky Way galaxy is the disk. It's our while the Earth is not flat, the Milky Way galaxy is. It is much wider than it is thick. And what we're seeing with the Milky Way galaxy is we are embedded within that disk, and we are looking through that disk. So, why do I not have a disk? I should invest in a disk. Let's look at this. Let's say this is the disk. And so imagine that this eyeglass case is actually round rather than rectangular. And so what we're seeing is we are inside this disk. So we're roughly halfway between the top and the bottom of the Milky Way galaxy. And so that cloudy plate, or that cloudy lane that you see, is if you were looking along the edge of the disk. Whereas, say, in the western part of the sky, you're looking, say, up, away from that disk. And so that's why there are fewer stars in that part of the night sky than in this part of the night sky. The Milky Way galaxy, the disk itself, is composed of stars of all different ages. You have some older stars, primarily near the center, but in the outer parts of the disk, you also have some younger stars. And younger stars tend to form preferentially in these open clusters than they do in these globular clusters. And so you have a lot of these things out there, from the Southern Beehive cluster to the basically any of these little circles, dotted circles. You have the Tweedledum cluster and also the Tweedledee cluster. These are in the constellation of Perseus, if I remember correctly. You have MGC 6871, which is the oh-so-romantic name of an open cluster that has been cataloged in the new general catalog as the 6,871 object. Again, astronomers are fabulous at naming things. And so when you look into the Milky Way galaxy, if you are open clusters are great objects if you have a good pair of binoculars or a small aperture telescope, something that on akin to like 4 inches to 6 inches. Because typically with those telescopes, your field of view is large enough that you can see all of these stars, all of these stars at the same time. You don't need to move your instrument around to get a good look at them, and it's a beautiful field. It's blue. You have these really nice blue stars that are distinguishable from all of the stars in the background, and again, they can come in all shapes and sizes. Another thing that we see when we look into the Milky Way galaxy is nebulae. Nebulae are clouds of gas. Because of the fact that in the Milky Way galaxy, most of the material is located within this disk, that not only includes stars, but also includes the building blocks of those stars. It includes the large clouds of dust and gas which these stars form from. And you can get just all kinds of nebulae that you can look at: the Funnel Cloud Nebulae, the Northern Coal Sack Nebulae, the Scutum Star Cloud. That one's a new one on me, and so forth and so on. But those are all within the Milky Way galaxy. What about all this stuff over here? Is there anything in the west that we could potentially be looking at? Well, let's zoom in a little bit. And when we zoom in, we find that yes, there are a few objects in the western part of the sky that we can observe. First, I'm going to start off with two of the biggest that you can, or three of the biggest that you can look at, and these are the globular clusters. Now, globular clusters, you will need a fairly low. You can, if you're really good at finding things using a pair of binoculars, you can see these objects. They're bright enough that you can see them. Globular clusters, if this is the Milky Way galaxy, globular clusters are in a spherical distribution around the galaxy. They are hundreds of thousands of light years away, so they are very distant objects. They're about as far out in the galaxy as you can potentially get. And so while there are millions of stars, or hundreds of thousands or millions of stars in these clusters, the clusters themselves tend to be a bit dimmer. And so you really need a good pair of binoculars or a fairly modest-sized telescope in order to be able to resolve them. And when you look at them, depending on the aperture of your instrument, if you're looking at it using a good pair of binoculars or a low aperture telescope or lower size aperture telescope, it's going to appear like a bluish blob. It won't be overly impressive, but you can definitely see it. You can definitely tell that there's something there that isn't a star, that isn't just a singular star. If you have a telescope, if you're lucky enough to get a telescope that's in the 6 to 8 inch range, you can actually start resolving these objects visually into clusters. You can literally see these stars all cluster around this center. It's still going to appear a bit blurry or a bit fuzzy, not blurry, appear a bit fuzzy because again, we are talking about looking at something that's hundreds of thousands of light years away. But you can definitively see them as individual objects. Now, the three that I'm going to highlight here is M13, the great cluster in Hercules. You have M3, and you have M10. And I should probably tell you what constellations these are in. And so M3 is very close to the constellation of Bootes. It is close to Arcturus. And M10 is, I should know what that constellation is. Whoops. Ophiuchus. Yes, that is Ophiuchus. So M10 is in the constellation of Ophiuchus. Interesting tidbit. Ophiuchus is technically a zodiacal constellation, which means there are people out there who are Ophiuchans. Probably didn't know that, did you? So there are people who are Aries, there are people who are Virgos, there are Cancers, probably a bad example, there are Tauri, and there are Ophiuchans. But no one talks about the Ophiuchans. Poor people. They have no future. They are literally a people without futures. No plates. I missed that one. I don't know when that was. That was a few minutes ago. So, sorry, Surf. I missed that comment. Kind of got off track. Another random thought that I had was Corona Borealis. Corona Borealis is a particular constellar, is a favorite of mine, in that I can only see the constellation of Corona Borealis when I'm in a dark sky, and not because it is a particularly dim constellation. It is, for some reason, if I can only see just a smattering of stars, for whatever reason, the pattern doesn't pop out at me. But if I'm in a really dark sky, and so if I'm in a reasonably cruddy sky, like a small town or something like that, I could be like, oh, all right, there's Orion, there's Lyra, there's Leo. Basically, I can walk you across the night sky very easily. But I can't find Corona Borealis for some reason, the Northern Crown. If I'm in a really dark sky, and because I have I haven't been in a really dark sky in some time, I get lost. There are just literally so many stars, and I have no idea where everything is, except for Corona Borealis. I can pick her out immediately. I'm like, oh, okay, there's Corona Borealis. So I can then say, oh, all right, if there's Corona Borealis and Biotes is right next to it, and then you have Hercules on the other side, and I can start piecing my way around the vast collection of stars that I can see. Oh, when you were looking for a disc. Oh, no, this is my office. So there are no plates. While I have a microwave, I've yet to bring in actual, silverware and stuff. So sadly, let's see. So, all right, getting back to this, and I know I apologize, this is very slipshod, but I'm just kind of going off the cuff. Now, when I zoomed in, I did notice something very fairly interesting. If you are someone who is interested in challenging objects or finding challenging objects, this is, let's see, let me actually do it this way. I am going to find it. Maybe. Search. Vesta. And Vesta is the largest, technically, astronomers have problems with naming things, but technically speaking, Vesta is the largest asteroid in the asteroid belt. That was previously held by Ceres, but Ceres got promoted to dwarf planet because Ceres is massive enough. Again, getting back to the spherical thing, if you're massive enough, you will take on a spherical shape. Ceres has enough mass to it that it formed into a sphere, and because of that, it is considered a dwarf planet. That and the fact that it hasn't cleared away it's not a bully. It hasn't cleared away its orbital path. But that's a subject for a Rob World episode. I have a bone to pick with the designation of planet. Vesta, on the other hand, Vesta is not spherical under its own gravity. It's not potato-y shaped, but it's distinctly not a sphere. It's really kind of oblongy. It's noticeably oblongy, and that is a technical terminology. But anyway, Vesta has a magnitude or brightness of 7.5, roughly. It is not a naked eye object. Our eyes can really only see down to about 6th magnitude, and that's if you're in a really dark sky. If you're in a really excellent dark sky, depending on the quality of your eyesight, you can probably push that down to around 6.2, maybe 6.5. My eyesight used to be good enough that I could get down to 6.5, but again, really dark sky in order to see that. Vesta doesn't even matter if you're in the middle of nowhere. If there isn't another human being for 1,000 miles, if you could ever find such a place on the Earth, you would never be able to see Vesta. So Vesta is an object that you would need a pair of binoculars in order to find. Now, the way to find asteroids is if you want to find it, you would probably use a program such as Stellarium. You would see where it is in the night sky. You would zoom in. And you would look at all of the nights, or you would look at the stars in the sky in this region, and you basically print out a map of what the sky without Vesta would look like for this region. And then when you looked in the night sky, you would try to find all of the stars that would normally be there, like Omega, Virgo, HR 4478. Woo, that's a beautiful name. HR 4464, HD 10717. I think he owes me money. 100 HD 100 518. Yeah, he's kind of a drag at parties. You don't get him drunk. Anyway, you would find all of these stars, and you basically figure out which one of these does not belong. You play the Sesame Street game. All of these stars, they match up to your star chart, but there would be one star that's new. and you could find it and you can look at Vesta. And the fun thing to do with asteroids like this is they move with respect to the background. So if you came back the next day, Vesta would be in a different position than it would be today. I'm going to move a little bit over because I'm noticing that if you move into Leo, you can get into what is the Leo triplet. Again, these are, there's a satellite. I have no idea what satellite. Oh, it's a NORAD satellite. It's a spy satellite. That's awesome. Yeah, I'm glad that Stellarium lets us know where the military satellites are. That's fantastic. Anyway, if you look into Leo, and you basically take the 3 stars and make up the back end of Leo, so you have the nice mane of Leo here, and then you go, and if you go to the back or towards the east, you can see Denobula, Zosma, and I can never remember this one, Shurton. If you see these, you can then navigate yourself to the Leo triplet. And these are 3 spiral galaxies that are in a cluster or a triplet. So these 3 galaxies are gravitationally linked to one another. And so these are, these are bright enough that if you have a good pair of binoculars, you can find these galaxies, and you can look at them. They would appear like fuzzy blobs. Again, they would be distinctly not star-like, but they would also distinctly not be cluster-like, star cluster-like. They would appear as their own separate thing. But again, if you were able to get a telescope, low power or a good power telescope, you might be able to see views that are reminiscent of this. You obviously wouldn't be able to see as fine a detail, but you could definitely see that the Hamburger galaxy was more oblong in shape. Basically, it's looking at the disk edge on, whereas the other 2, M65 and M66, are spiral galaxies, very much like the Milky Way galaxy, but they are more face-on. We're looking down onto them rather than looking along the edge of the disk. And so I'm going to zoom back out. And what I'm going to do now is I'm going to show what the night sky is going to look like. And the other thing you can find, this is the double cluster in Perseus. So Perseus is over here. Tweedledee and Tweedledum are in Sagittarius, it looks like. Where did they go? Where did Tweedledee and Tweedledum go? Oh, no, sorry. They're close to Aquila. So what I'm going to do now is I'm going to show you what the sky is going to look like in Fairfax, or on the eastern seaboard, in 6 hours. So if I were to go to here, let's advance the time by 6 hours. 1, 2, 3, 4, 5, 6. It is now 4:30 in the morning. I don't know why I'm looking over there. The camera's here. And what we can see is that the stars move from east to west, as one would expect. So if you are interested in looking, and so we have a couple of more interesting objects, or potentially interesting objects, depending on your tastes. In the southern part of looking south, what we can see is we have the moon, which is, unfortunately for stargazing, rather full at the moment. It is, I believe, a day or so out of the full phase. Let's see, can I find the illumination? It is 96.5% full, and it is beginning to wane. It is getting smaller over time as we move along in the next 2 weeks. So the moon, going from the beginning of July to the middle of July, will go from a full phase to what we call a third quarter phase, where you will only be able to see the left-hand side of the moon, and you can only view it from in the mornings. But also, trailing behind, dutifully behind, I said dutifully, dutifully behind the moon, you have Saturn and Jupiter. These are two beautiful objects to look at. They are conspicuous in the night sky in terms of trying to find them naked eye, because if you can find the moon, if you look behind the moon or towards the eastern part of the sky, you will see two very bright objects, fairly equally spaced behind it. At least right now, that will change as we move forward. But you will see these two very bright objects in the same line along with the moon, and these are um, much brighter than the stars around them, and they don't twinkle. Stars twinkle because of the atmospheric effects, and I will be putting out a Rob World episode which talks about what twinkling is. But twinkling only really affects objects that are so small as to be point-like in the night sky. Planets are sufficiently disk-like. So, for example, Jupiter has an angular diameter right now of around 45 arc seconds, or if you want to round up, 1 arc minute, meaning that its diameter is the same as if you took the full moon and you split it into 30 equal slices. One of those slices would be basically the size, the angular size of Jupiter. And so it's big enough that it doesn't the light coming from one edge of the planet as opposed to the other edge of the planet, they do not get basically bandied about nearly as much as if it were coming from a single point source. So, as I like to say, if you look up the night sky and it twinkles, it's a star. If it doesn't twinkle, it's a planet. If it blinks, it's a plane. So you have Jupiter and Saturn. Saturn is significantly smaller. It's roughly around half the size of Jupiter. It's around 18 arc minutes. And so for the next couple of weeks, Jupiter and Saturn, if you're interested in looking at planets, again, these are both objects that are very nice, nicely viewed through binoculars or small telescopes. These can be viewed at the beginning of June or beginning of July. These are viewed best around 4 o'clock in the morning. And again, as we get to further along in June, they will become available earlier and earlier. And again, we also have another of M2, which is another globular cluster. The Perseus cluster is another globular cluster that you can look at as well. The last thing I will say before I move on in date is in Cygnus. Again, this would be a binocular, or a very nice binocular or small telescope object. There it is. Is a binary star called Albireo. Which, come on, I know this is in here. Oh, there it is. Just misspelled it. Albireo. There we go. That's the foot of the cross. Albireo is a binary star that you can see with your naked eye. But because they are so close to each other on the sky, it only appears as one star. It's not resolvable into two stars unless your telescope is sufficiently large. This is what we call, when you hear about the Rayleigh criterion, when you hear about the angular resolution of objects, this is what it's talking about, is that the human eye has an angular resolution of about 1 arc minute, meaning it cannot see detail on size ranges, angular size ranges, less than an arc minute. So even if the moon were, even if Jupiter were 1 arc minute in size, rather than 45 arc seconds, roughly 3/4 of that, We still wouldn't be able to see the great red spot because the great red spot is much smaller than obviously the entire size of Jupiter. We wouldn't be able to resolve any of the surface features on Jupiter. It's also the reason why, while we can resolve Mare, the dark stains on the moon, while looking at it through our eye, we're not able to resolve any of the craters on the moon because our angular resolution is insufficient simply using our eyes. But if you use a pair of binoculars or a low aperture telescope, that is sufficiently large enough that you can actually start to see individual features. And with Alberio, what you see is, if we zoom in close enough, you see that this star is not in fact one star, but two. There is a bright, and unfortunately, Stellarium really doesn't do this justice. I am a University of Florida grad, so we used to refer to this as the Gator Star. Go Gators. This primary star is very bright, very red, or rather orange, and this star is very bright and very blue. They correspond to the opposite ends of the temperature spectrum in terms of stars. That red star, that or orangey star, that has a surface temperature of around 3,000 Kelvin. Or 4,000 Kelvin, whereas the blue temperature star the blue star has a surface temperature around 40,000 Kelvin. Once you start getting into that range, the conversion between Kelvin and Fahrenheit is pretty much the same. Close enough for horseshoes and hand grenades. So you can think of it as 3,000. The orange one is roughly 4,000 degrees Fahrenheit on surface, whereas the blue giant is roughly 10 times as hot as the red one. So yeah, they are fairly, while they appear almost equally bright, they are drastically different in their structures, their temperatures, and so forth. And so it's just a really pretty binary. I highly recommend you find, and it's really easy to find. All you have to do is just look at, or just find Cygnus, the swan. Again, it is the Northern Cross. You can find, this is Deneb. Whoops, that's Deneb. Vega, Altair, you have the Southern Triangle. So once you find the Southern Triangle, you can find Deneb. And then once you find Deneb, you can find the Northern Cross. And the foot of the cross, or the foot of Jesus, is Alberio. And if you look at it using, like I said, a good pair of binoculars, you can resolve that is two stars instead of one star specifically. I need to make a note of the time. Okay. And so that is what the night sky will look like in Fairfax, or the eastern seaboard of the United States at 4 a.m. Now I am going to just go ahead and jump over to going to change the location. If I can remember where. Time and date, location, there it is. And I'm going to choose a random location of Cork, Ireland. Because that's close enough to the UK and all that. So I wanted just a sufficiently distant enough part of the Earth to illustrate a certain phenomenon. Now what I'm going to do is I'm going to change the... I don't know if this is actually what Cork looks like. I guess somebody would have to tell me if that's what Cork looks like. Somehow I don't think so, but let us change because time zones are a thing. Kind of have to make sure that it's nighttime. So let's go back to the 25th and And we'll put it back to, oh, you can see that at 10:40, I was not aware of this. Cork, Ireland is so far north that at 10:40, it's still twilight. So we're actually going to have to go to 11:40. That I did not know. You learn, even I can learn something new every day. Um, and so this is essentially the same time as now, roughly the same time as now. But you can see that and I'm going to orient this such that east is actually on the left and west is on the right, as we saw before. And we can see that with Ireland, as with Fairfax, essentially their view is pretty much the same as ours, with a slight difference in that if you remember back, if you're on the eastern seaboard, at roughly about the same time, all these stars were actually more towards the east. And so all the objects that I was talking about before are now, if you're in Ireland, or in England, for example, or the roughly western part of Europe, Western Europe, all the objects that I was talking about at the very beginning of the night will be higher up in the night sky, will pretty much be, instead of being in the eastern part of the sky, they will be directly overhead or very close to directly overhead. But you should be able to see pretty much the same sort of view. There is nothing up that is there's nothing in the night sky that you wouldn't be able to see from the eastern seaboard to here. Again, the stuff in Leo, if you are interested in looking at those galaxies, if you do have a telescope and are able to actually look at those galaxies, or if you want to find Vesta, you want to do it early. You want to get on those targets sooner rather than later, because they're going to set within the next hour or so. So unlike in the States, on the eastern seaboard of the United States, when you have a few hours to look at these objects, while you're in Ireland and UK, you will only have about an hour to observe these objects before they set. On the positive side, you don't have to wait nearly as long to see the moon and Jupiter and Saturn. Well, I'm going to take that back. I'm going to walk that statement back. Oh wow, I am surprised by how few hours of darkness you guys have over there. God, that's north. The other thing is because you all are so north, Jupiter and Saturn, you probably already know this. Jupiter and Saturn are far lower on the horizon than they are here. And so while Jupiter and Saturn in Fairfax they can get roughly about 45 degrees up. Here, not so much. I'd say probably 30 degrees, 20. I can figure that out, but I'm too lazy to do it at the moment. But you can see that around 3 o'clock in the morning, they are coming up. They are pretty much just rising out of the east. Again, you still have that same orientation of Moon, Saturn, Jupiter. And you can see that as we move on to later as we move on through, as you can see, this also occurs on the eastern seaboard, or anywhere really. As you move in date, the moon we're changing in date, but not in time. So if you were to, this simulates the idea that you come out to the field at the same time. So this is what it would look like tonight. This is what it would look like tomorrow. The next day, you can see that Saturn and the moon get very close to each other. The moon on the 28th will appear to be pretty much in between Jupiter and Saturn. On the 29th, it will be very close to Saturn, or very close to Jupiter. And as we move into the middle of July, and as I was saying before, all the objects that I've highlighted, they will be in the night sky, just higher up in the night sky when you go out at the same time. So if you routinely go out to see the night sky at, say, 10 in the evening, and you look at, say, the star Alberio, the binary star Alberio, the next time you come out, the next night you come out to look at it, it's going to be higher up in the sky at 10 o'clock in the evening, and it's going to progressively get higher and higher as you go up. Now, one thing I will be remiss with saying that without pointing out is the Andromeda Galaxy. The Andromeda Galaxy is the only galactic object that is essentially, well, not essentially, is naked eye. You need a dark sky in order to see it, but you can see the Andromeda Galaxy. The light coming from the Andromeda Galaxy can be detected by the human retina, which means if you wanted to know what is the farthest that your eyes can see into the universe, they can see roughly around 2.5 million light years into the universe, because you can see the Andromeda Galaxy, and that's roughly its distance away from us. Granted, the reason why you can see it, why you can see something that's so immensely far away, is because you're looking at a galaxy that is very comparable, and although actually slightly more massive than the Milky Way itself. You're talking about a galaxy that contains roughly around 500 billion stars, all located in that tiny patch of the sky. Now, as naked eye objects go, it's going to be fairly it's going to look like a smudge. It's not going to look all that pretty. But as you magnify it, as you get larger and larger, or as you get it larger and larger, using binoculars or telescope, you can see much more detail. If it's a large enough telescope, naked eye, you can actually start to see some of the dust lanes that are inside the star. Or if you're lucky enough to have a telescope such as mine, you can take a picture that looks like this. Let's see, do I have... Let's see here. Let's not do that. Let us stop sharing screen. Howdy, y'all. And let me see if I can bring one up. I like this image. I've looked at this, or highlighted this image before in a Rob World episode, but I'm going to just pimp it out again. Oops. And it will look something like that. And so this is an image that I took of the Andromeda Galaxy. Actually, technically speaking, it is 4 images that I have mosaicked together. And that is, if you have a good sized telescope and a digital camera like a DSLR, you can take an image like this, and possibly even take an image like this in color, and you can see that there are. I want to bring screens around. You can see that the disc-like shape of Andromeda, this is the dust lanes here are located within that disc. You have these, you can almost trace out spiral arms using these lanes as guideposts. And then you have that dark, dense center of the galaxy there. All right. Well, I think that is all I wanted to share with you all. Surf, if you have any questions, I will be happy to answer them. Getting all discombobulated. I will be happy to answer them. I apologize for weather. I was going to apologize for the weather, but that seems a bit silly. Um, yeah, unfortunately, the weather really didn't cooperate. I'm really hoping to be able to one of these nights actually show you the beautiful images that we can get using the point 0.8 meter telescope, like the one, well, like that Andromeda image that I just showed you, and be able to show you how I do that. And while I'm doing that, provide an explanation as to what those astrophysical objects are. And in the future, I think I will have a better backup plan. So I'm not just rambling incoherently about various things. So, but thank you all for watching. Thank you for those of you who have. Oh, cool. That's awesome. Thank you, sir, for hanging out with me. And yeah, look forward to doing more of these and trying to share my love of astronomy with everyone else. So peace out, and always remember, no matter how dark it gets, you are always stardust. Good night.